Imagine you are handed a $3.8 billion budget.
Okay, that is a pretty good start to any day.
Right. But here's the catch. Your mission is to build a massive 1 million square foot airport terminal.
Still sounds like a standard mega project, for a major contractor.
Well, it is until you factor in that you have to build this 30-gate terminal on reclaimed land that could literally turn to liquid in an earthquake.
Yeah, that complicates things immensely.
Oh, and you have to do all this massive construction right next to an active runway with live flight operations.
Which is basically an impossible engineering scenario.
Exactly. But that is exactly what the Turner-Flatiron joint venture and Hensel Phelps did for San Diego's new T1 Replace program. It's just a masterclass in constrained construction.
It really is. I mean, the physical execution alone is a marvel.
So today we're doing a deep dive into how they pulled off the impossible. We've got project intelligence from Smart Business Automator, along with some heavy engineering reports on the project.
And we're going to explore all of it, from, extreme foundation engineering to a brilliant structural innovation that eliminated 100 columns.
And obviously how they used artificial intelligence to orchestrate the whole thing. So let's start with the ground, because before you can build up, you have to secure the earth.
Right, and when the earth is essentially a liability, that's your first major hurdle.
Yeah, San Diego's terminal sits on liquefiable reclaimed land in a major seismic zone.
Which is terrifying. Under severe seismic loading, the pore water pressure in those saturated soils increases, and the soil literally loses its shear strength.
So it's basically like trying to anchor a massive concrete fortress onto a giant wet sponge.
That is a perfect analogy. You cannot rely on that immediate subrate at all.
Right. And to stop this thing from sinking, the reports show they had to drive 3,000 piles up to 90 feet deep.
Wow, 90 feet, that's what, a 9-story building underground?
Yeah, pretty much. So how does driving piles 90 feet down actually solve the whole liquid earth problem?
Well, the mechanism relies on bypassing that liquefiable layer entirely. Those 3,000 deep foundation piles operate through a combination of end bearing and skin friction.
Okay, break that down for me. What does that mean in plain English?
Sure. So by driving them 90 feet down, the engineers penetrate the loose wet soils and basically anchor the piles into the dense, non-liquefiable bedrock deep below.
Oh, I see. So the foundation is gripping the stable earth underneath the sponge.
Exactly. So during an earthquake, if that upper 30 feet of soil temporarily loses its bearing capacity, the vertical loads of that massive terminal are already safely transferred deep into the stable strata.
That makes sense. But the piles only handle the vertical load, right? Like the weight pushing down. The ground still needs lateral containment, so the whole site doesn't just shift sideways.
Right. And that brings us to the retaining walls. They built over 30 of them using a technique called jet grouting.
I was reading about this. It's not just pouring concrete into a trench, is it?
Oh, no, not at all. Jet grouting is an incredibly violent, highly controlled process. They advance a specialized drill string down to the required depth, and as they slowly pull it back up, they inject a cementitious grout mixture at extreme pressures. I'm talking often exceeding 400 bar.
Wait, really? 400 bar? That's insane pressure.
It is. The kinetic energy actually physically destroys the soil matrix. It shears the native dirt particles and mixes them immediately with the grout right there in the ground.
So the native dirt basically becomes the aggregate for the underground wall.
Exactly. It forms a continuous, uniform column of what we call soilcrete. And by overlapping these columns, they build these massive interlocking retaining walls.
Forming like a rigid subterranean bathtub.
Yes, a bathtub. It stiffens the entire soil block so that it behaves as one cohesive unit during an earthquake. It drastically reduces the chance of the ground settling unevenly.
Okay, so they've got this subterranean bathtub and 3,000 piles. The ground is secure, but that sets a really strict boundary for the rest of the project, doesn't it?
It absolutely does. Every single pound of steel and concrete you add above ground becomes a point load on those piles.
Right, you can't just slap a heavy conventional concrete frame on top of this and call it a day.
No, if you did that, the foundation couldn't absorb the mass sufficiently without, catastrophic cost overruns.
So the structural engineers had to get creative, and we're talking about MKA here, the same firm behind Apple Park.
Yeah, MKA is top tier. And working with the architect, Gensler, they had to totally rewrite the terminal's skeleton.
And this is where we get into the buckling restrained braces, or BRBs, which, by the way, the numbers on this innovation blew my mind.
They are staggering. By using BRBs, they completely replaced conventional columns.
Yeah, I have the stats right here. They eliminated 100 columns. They cut 40% of the steel tonnage, saved $58 million, and reduced embodied carbon by 30%.
It's just a massive win across the board.
Wait, I need to pause here, though. Usually, making a building earthquake-proof means adding more materials, right? Making it bulkier, spending way more money.
That's the conventional thinking, yeah.
But you're telling me that by using these specific braces, they took away 100 columns, made it stronger, and saved $58 million.
I know it sounds counterintuitive, but yes. And it all comes down to the elegant physics of a BRB.
Okay, explain the physics to me, because in a standard steel frame, braces work great in tension when they're pulled, right?
Right, they're basically cables at that point.
Yeah.
But the moment the seismic wave reverses and pushes on them, putting them into compression, they tend to buckle.
And to stop them from buckling, you normally have to use massive, thick pieces of steel.
Exactly. But a BRB subverts that failure completely by separating the load-bearing element from the flexural element.
So it's two separate parts doing two separate jobs.
Exactly. At the center of a BRB is a highly ductile, yielding steel core. It's designed to stretch and compress, absorbing massive amounts of energy during an earthquake.
Okay, but wait, that core is encased in a concrete-filled steel tube, right?
It is, yeah.
So if the yielding steel core is embedded in concrete, wouldn't the friction during compression just transfer the load to the outer casing and cause the whole thing to snap anyway?
You'd think so, but here's the brilliant part. The mechanism that prevents that failure is called the unbonding layer.
The unbonding layer.
Yeah, it's this microscopic gap, usually filled with a specialized polymer or mastic material that sits right between the steel core and the concrete.
Oh, wow.
So this layer prevents any stress from transferring between the core and the casing. When the building sways and the brace gets compressed, that steel core is free to slide and yield within the tube.
So the concrete casing's only job is just to hold the core straight so it doesn't pop outward?
You got it.
Yeah.
It physically prevents the core from buckling. This means the core can absorb energy in compression just as efficiently as it does in tension.
That is wild. And because each individual brace is so optimized, the overall building needs way fewer of them, hence eliminating 100 columns.
Right. And reducing the steel directly translates to that massive 30% cut in embodied carbon. Less steel means less manufacturing, fewer deliveries, less crane time.
But catching an opportunity like this to literally rewrite the structural skeleton of a $3.8 billion project, you have to catch that incredibly early, right?
Oh, extremely early. Usually in the schematic design phase, before architectural footprints are locked in.
And this is where advanced document intelligence comes into play because, human engineers can't manually read through 5,000-page spec books and historical cost models fast enough to propose a $58 million pivot.
No, it's a massive bottleneck. And that's why teams use platforms like Smart Business Automator. It extracts critical details from complex specs so teams don't miss these million-dollar savings.
So Smart Business Automator can basically ingest all the architectural drawings and local codes at once.
Yeah, exactly. By querying that unstructured data using natural language, the engineering teams can instantly model alternatives. The AI highlights the cost differences between a standard frame and a BRB system in real time.
Which allows the contractor to actually present a fully costed alternative to the client before it's too late.
Exactly. It's an invisible infrastructure of data working alongside the physical engineering.
Okay, so the BRBs solved the weight and the cost issues on paper, but actually executing it in the real world is a totally different beast.
Oh, without a doubt. The logistics of the new T1 Replace program are just as complex as the structural physics.
Because they have that strict one active runway constraint, every single crane swing, every concrete pour has to be phased around live 737 flights.
Right, you've got commercial aircraft creating wake turbulence and noise pollution mere feet away from massive, heavy civil work.
Honestly, this sounds less like construction and more like performing open heart surgery while the patient is running a marathon.
That is pretty much exactly what it's like. You have 25,000 construction jobs associated with this project. It's a $4.5 billion economic impact.
The coordination required to manage 25,000 workers alongside live airplanes is just staggering.
And you can't afford a single delay. If a steel delivery arrives off schedule and bottlenecks an access road, it doesn't just delay the painters. It threatens the operational continuity of the entire airport.
Which cascades into the National Airspace Network. A delayed truck in San Diego could mean a delayed flight in Chicago.
Exactly. And on top of all that, they're pursuing LE Gold certification.
Right, the sustainability targets. And one of the requirements for that is building a 900,000-gallon stormwater capture system.
Yeah, try excavating and installing a subterranean system of that magnitude right in the middle of a site constrained by live flight operations.
The schedule synchronization for that has to be flawless. How do you even manage the interdependencies? Like, you have stormwater excavation, pile driving, and steel erection all happening at once.
Well, a static schedule updated once a week just doesn't cut it when conditions change hourly. You need dynamic schedule risk detection.
And this is where Smart Business Automator comes back into the picture, right?
Yes, exactly.
Okay.
To avoid catastrophic bottlenecks, the AI evaluates project activity to flag delays before they even happen.
Because it's running continuous Monte Carlo simulations in the background.
Right. It models thousands of possible project outcomes based on historical data. So say the AI detects that the deep excavation for the stormwater system has a high probability of clashing with the BRB steel shipment because of rainstorm.
The system flags that conflict spatially before the trucks even arrive on the tarmac?
Exactly. You give the project managers the ability to reroute logistics proactively.
But wait, if I'm a project manager overseeing just a fraction of those 25,000 workers, aren't I just drowning in daily logs and change orders? How does an AI project assistant actually change my day-to-day on a site like this?
Well, that's the invisible infrastructure we were talking about. Instead of hunting through nested folders for answers, the AI acts as a project-aware assistant.
So when a spatial clash is identified, and they have to generate all those requests for information or RFIs between the field supers and the architects, the AI helps manage that.
It does more than manage it. Smart Business Automator uses historical context to instantly generate draft RFI responses.
Oh, wow. So it's literally writing the first draft of the technical response.
Yeah, and it also has computer vision models trained specifically on heavy civil construction.
Wait, really? How does that work in the field?
Say a superintendent snaps a photo of a really complex rebar grid for one of those jet-grouted retaining walls. The AI doesn't just see a picture, it uses object detection to identify the rebar gauge, the spacing, the splice lengths.
And it checks that against the digital model.
Exactly. It cross-references the visual data against the specific structural engineering codes. If something is out of compliance, it flags it immediately before the concrete is even poured.
That is incredible. And does it talk to the financial side of the project, too?
It does. It uses seamless API integrations with the existing accounting and ERP software. So when the AI identifies a schedule shift from the daily logs, it automatically updates the cost forecasting models,
giving the executives real-time visibility into the budget variances. No more manual data entry from a clipboard to an email to the accounting software.
Right. It completely eliminates that latency.
Okay, but I have to ask the obvious question here. A common critique of AI in engineering is the risk of hallucination, right? Generating answers that sound right but are technically totally wrong.
Oh, absolutely. And on a $3.8 billion project, the AI cannot afford to guess.
Right. If a PM asks the AI about the curing time for the jet grouting mix, how do we know the AI isn't just making up a plausible-sounding number?
It's a great question. The system prevents that by using a framework called Retrieval Augmented Generation, or RG.
Okay, RG. How does that stop hallucinations?
Because the AI is not querying the open internet. It is strictly bounded by the project's specific data environment. It indexes the approved architectural drawings and geotechnical reports into a database.
Ah, I see. So when the PM asks about the curing time, it's only looking at the verified documents.
Exactly. It retrieves the exact paragraph from the approved submittal, cites the source, and generates the response based strictly on that verified data.
So Smart Business Automator is essentially the nervous system that allows these companies to scale up and handle impossible constraints without dropping the ball.
That's a great way to put it. It reallocates human capital. Instead of managing a massive paper trail, the PMs can focus their cognitive energy on actually building the terminal.
Which is how you orchestrate something this massive without delaying a single flight. It's fascinating when you look back at the causality of the whole project.
Oh, it really is a chain reaction of problem solving.
Right. The liquefiable earth forced them to use 3,000 deep piles and those jet-grouted retaining walls.
And then that heavy foundation meant they couldn't use standard columns.
Which forced them to innovate with buckling restrained braces, cutting 40% of the steel and saving $58 million.
And delivering all of that next to a live runway required advanced AI tools running predictive simulations to keep 25,000 workers moving safely.
Every single solution was born directly from a severe constraint. And honestly, this should completely alter how you, the listener, look at commercial architecture.
I agree. It really makes you question the status quo.
Absolutely. Because if a simple shift to buckling restrained braces can eliminate 100 columns and cut 30% of the carbon in a massive airport terminal, look at the high-rises in commercial buildings in your own city.
Well, for sure. How many of them are massively over-engineered with traditional heavy steel?
Right. Hiding millions of dollars in wasted materials and carbon emissions right in plain sight, just because they didn't have extreme constraints forcing them to innovate.
People default to what is established because it feels less risky. But the real risk is absorbing all that unnecessary cost and environmental impact.
Exactly. So here is your takeaway. If you're involved in real estate development or structural design, you need to challenge those defaults. Go study the specific physics of the BRB innovation. Ask your structural engineer about it on your next project.
Yes, push the envelope, and you also need to evaluate the computational tools you're using.
100%. You cannot build the next generation of infrastructure using analog spreadsheets. Go visit smartbusinessautomator.com to analyze how they are actively dismantling administrative bottlenecks. Because the future of construction isn't just about moving dirt. It's about moving data just as efficiently.
Beautifully said. That is it for our deep dive today. Let us know what you think of BRBs and AI in construction. Like, share, comment, and subscribe, and we'll catch you on the next deep dive.